Welcome to capacitance. We've seen before the phenomenon of a charged object interacting with other charges. The most common example of this would be static electricity. If you rub the balloon against a jumper, then the balloon and the jumper become charged. You can then do things like stick the balloon to the wall. Let's have a look at a simulation that explains this phenomenon. So here we have the balloon, and if we rub it on the jumper, it can stick and is attracted to the wall. Notice that if I pull it away from the wall and release, it moves towards the wall. The reason for this is because everything has positive and negative charges. The wall has positive and negative charges, as does the balloon, as does the jumper. Normally, these positive and negative charges occur in the same quantities. Everything is neutral. The number of positives is equal to the number of negatives in all objects. But some materials are more attractive to these negative charges, these electrons, than other materials. And in this simulation, the material that the balloon is made from is more attractive to electrons than the wool of the jumper. So if I rub the balloon against the jumper, then electrons are attracted more to the balloon than they are to the jumper. And now the balloon has a charge. And when I let go, that negatively charged balloon is attracted to the positively charged jumper. If we make the balloon very strongly negatively charged and then bring it close to the wall, then we will see why the balloon sticks to the wall. As we bring it closer, observe the negative charges within the wall. They are repelled from the balloon. Recall that the positive charges essentially are the nuclei of atoms, and the negative charges are the electrons. So the electrons are free to move, but the positive charges are not. So as we bring the balloon closer, the negative charges are repelled deeper into the wall, leaving a positively charged surface. And it is that surface that the balloon is attracted to. So here we have a charged object being attracted to another charged object. And this forms the basis of our understanding of capacitance. So we've just seen how an object can become negatively charged and how it can repel those same charges in the surface of the wall and be attracted to the remaining positive charge there. This idea of having a positive charge on one object, a negative charge on the other, and an electric field between them is the basis of capacitance. Another example of this sort of effect are Franklin bells. In the center is a string holding a metal ball which can conduct electricity and become positively or negatively charged. On the left side, we have a dome which will resonate when struck, and it is connected to an electrode. On the other side, we have another dome which is connected to another electrode. If one dome is made positively charged and the other dome is made negatively charged, then we can get this bell ringing. If we push the ball in the center so that it touches either the negative or the positive electrode, then this bell will start to ring. Let's push it to touch the negative electrode. If we do that, then the ball becomes negatively charged. It is then repelled away from the negative electrode and attracted towards the positive. When it comes into contact with the surface of that positive bell, the negative charges inside are lost and the ball becomes positively charged. It is then repelled away from this surface and towards the negative electrode. And this repeats backwards and forwards at a high frequency, causing the bell to ring. There's a very famous example of one of these in Oxford University. This Franklin bell is very similar to the situation we had with the balloon and the wall, where we have a positive charge on one side and a negative charge on the other. And this forms the basis of a capacitor. A capacitor is two conductors, one side connected to a positive terminal and the other side connected to a negative terminal. And each one of these becomes charged. And between them is an electric field. Here we can see an example of a capacitor, and inside we can see one of the plates, the other plate, and an insulating material in between called a dielectric. We will look at the structure of a capacitor in a later video. Here's a photograph of some examples. The height here is about 1/2 centimetre tall. This capacitor is 47 microfarads. The farad is the unit of capacitance. Capacitance is the charge per voltage. So if we have a look at this circuit here, the voltage of the power supply is dropped across the capacitor, and the greater the capacitance of this capacitor, the more charge can be stored per volt. The unit of capacitance is the farad, for charge it's the coulomb, and for voltage it is volts. In SI units, the farad is per kilogram, per metre squared, seconds to the power 4, and amps squared. You don't need to know that, but you should note that it's a very complex unit. Let's do a calculation for this 47 microfarad capacitor rated at 50 volts. The charge that it can store is given by this equation, capacitance multiplied by voltage. The capacitance is 47 microfarads multiplied by 50 volts gives us which gives us 2.35 millicoulombs. This is a pretty typical size for a capacitor. You are unlikely to see any capacitors that don't have a small prefix. So on the scale of whole farads, those are very rare. Usually they are nanofarads or microfarads. Even the largest capacitors that you're likely to come across in the classroom are still likely to be milli or micro.